Hi everyone, welcome to the new session. In today's session, we are going to learn about the types of relations. Okay, so let's get started. Okay, so there are several types of relations, and we are going to discuss all of them one by one. Okay, so yesterday, we defined in the yesterday session, we defined the relation and we said that a relation from non-void set A to the non-void set B is the Cartesian product of AB, right? So then we had discussion that whatever relation are you going to get from set A to set B. So relation is basically the set of ordered pairs. So if you look at the set of ordered pairs, then you will find that those ordered pairs in the relations are the subset of the Cartesian product. Understand? So we had a in-depth discussion on that. Okay, today we'll start with the types of relation. Okay, so first we'll start with our first relation that we are going to start is our empty relation or void relation. Okay, so here I'm writing empty or void relation. Okay, what does it mean, empty or void relation? I hope it is visible to you. Yes. Okay, so empty or void relation. Okay, so I would say that a relation defined from set A to set B, let's say that this is my set A. Okay, so here this is my set A and this is my set B. Okay, and in set A, I have elements 1, 2, 3. And in set B, I have elements A, B, C. Okay, so the relation from set A to set B, which is written as this. Okay, relation from set A to set B. Okay, so the empty or void relation, it means that a relation from non-void set A to non-void set B is said to be empty or void relation if no elements of set A are related with any elements of set B. Means that you won't see any elements of set A related with the elements of set B. Understand? So let's say that here we have this relation from set A to set B. Okay, and this relation is empty relation. Okay, so I'm writing here that in empty relation, relation is said to be empty or void if no elements of set A, of course non-void set A, are related to any elements of set B. Okay, so then we will say that the relation is empty relation, means that you won't see any elements of your set A related to any element of set B. Okay, so when there is no relation between the elements of set A to set B, then it means that we have empty or void relation. Okay, so in that case, we will say that our relation, it is empty. See here, empty, or other way to write it, or our relation is null. Understand, it's void. Okay, so empty relation, as the name says, that there is no relation, void relation. Okay, no elements of your set A is related to any elements of set B. Okay, so quite simple. All right, now next we are going to talk is uh, universal relation. Okay, universal relation. Okay, universal relation. Now we'll see what is universal relation. Now we'll explain the universal relation with the example, and then we'll come to the definition. Okay, so let's say that I have two sets. Okay, same non-void set. Here I have set A, and here I have non-void set B. All right, so here in set A I have elements 1, 2, 3. Okay, and in set B I have elements A, B, and C. Okay, now R is a relation defined from set A to set B. Okay, so I will say that R is a relation which is defined from set A to set B. This is how we represent relation. Now, this R is said to be universal. It is said to be universal when each element, again I'm repeating it, the relation R is said to be universal when each element of A is related to the every element of set B. Each element of A is related to the every element of set B. So what does it mean? It means that 1 is related to A, 1 is related to B, 1 is related to C, 2 is related to A, 2 is related to B, 2 is related, sorry, 3 is related, 2 is related to C. Yes, 2 is related to C. 2 is related to 2 is related to C. Then 3 is related to A. 3 is related to B. 3 is related to C. Okay, means that each element of this set is related to every element of your set B. So if that's the case, it is said to be universal. R is said to be universal if each element of set A is related if each element of set A is related to every element of set B. Okay, so here I can say that here, okay, if I have to write the relation in set builder form, here I can say that R, it's going to be A, B, such that A belongs to set A and B belongs to set B. Okay, so R is going to to be the set of ordered pairs AB, where A belongs to A and B belongs to set B. Okay, now if that thing happens here, so from here I can say that R, it's going to be 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C. Okay, now look at this thing. Okay, this is a relation. This is universal relation. If you look at the set of all the ordered pairs in this universal relation, we can figure it out that this is exactly same as A Cartesian product B, right? Here, the equivalence, sorry, the universal relation here, it is same as A Cartesian product B, because here each element of this set is related to the every element of this set, okay, which is same as A Cartesian product B. Okay, now try to understand this point. If if I define this universal relation from set B to A, okay, this is relation from set B to A, or 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 okay, fine, okay, I don't want to mix things here. Okay, so if R is the universal relation defined from set B to set A, so here I will say R is a relation defined from set B to set A. So then from here you will see that the universal relation, this universal relation R, it's going to be same as B Cartesian product A. I hope you understand it. Okay, so universal relation between two sets, it's nothing, but it is the Cartesian product of two sets, right? So I hope you understand it. Okay, is it visible? All right, yeah. Okay, now come to the next. Let's go to the next one. Okay, so next one, this was number one, number two, number three. Okay, so number three we have, oh, next number three we have okay, so number three we are going to take, number three is our number three. Relation number three is the inverse relation. Inverse relation, okay, or inverse of a relation, okay, inverse relation. Now let's take two sets again. Let's say that this is my set A and this is my set B. Okay, and I have same elements 1, 2, 3 in set A, and I have A, B, C in set B. Okay, and R is the relation defined from set A, non-void set A to the non-void set B. So here R is relation from set A to set Okay, so here this R is a relation such that the element, let's say that this one, it is paired or mapped with B. This one, it is mapped with C. 2 is 2 is not mapped with any elements of this set. 3 is mapped to A, and 3 is mapped to C. Okay, so R is a relation. Okay, R is the relation defined from set A to set B. Okay, so here I can say that from here that R, it's going to be the what ordered pairs I'm going to take here. 1 is related to B. Okay, so 1B, right? Then 1C, right? Then 3A, right? And 3C, right? 3C. Okay, so I took 4 ordered pairs because these are the ordered pairs that satisfies the condition, that relation put on these two sets. Understand? Okay, so if R is a relation defined from non-void set A to B, then inverse relation of this, the inverse relation of this is going to be inverse of relation R. It's going to be R inverse. Okay, this is a way to represent inverse relation. Okay, so I am finding the inverse of R. So inverse of R, it's going to be R inverse, and this relation, this inverse relation, it's going to it's going to it's going to be defined from set B to set A. Okay, see here, our relation was defined from set A to set B. The inverse of this relation is denoted by R minus 1 here, and this relation is defined from B to A. Okay, so we are just doing the inverse. Understand? So if this is R inverse, then see here, what does it mean? Same set A, same set B, and this R, now see here, R was the relation from set A to set B. So R inverse, now see here, this is R inverse. It will be from set B to set A. Understand? And here I had elements 1, 2, 3, and here A, B, C. Okay, so in inverse relation, see here, A is mapped with, as A was not mapped, A was mapped with only 3, right? So A was mapped with 3. Okay, and B was mapped with 1, B was mapped, 1 was mapped with B. So here we will just do the opposite. B is mapped to 1, then here C is mapped to 1, C is mapped to 1, then 3 was mapped to A and C, so C is also mapped to 3. Okay, so what's going to be R inverse? Okay, it's going to be uh, A, it's going to be A, A, A3, right? Then B1, then C1, right? C1 and uh, B1, C1 and C3. C3. Okay, so if you look at both these relation, this is inverse relation. Now you can see the ordered pairs, they just have switched the places. The places are flipped. Okay, see here 1b, here b1, here 3a, here a3, here 1c, here c1, here 3c, here c3. Okay, so our relation, it was defined from set A to set B. See here, this is our relation defined from set A to set B. If you have to find the inverse, then it has to be from set B to set A. I hope this thing is clear to you. Okay, so let's go to the next one. Okay, now the next one is your identity relation. Okay, next one is your identity relation. All right, so the next one is number 4, identity relation. Identity relation. Okay, now we will start with the definition of this relation, because the definition is very important, and it says that a relation is said to be the identity relation if and only if every element of set A, of course non-void set A, is related to itself and only to itself. Okay, so a relation is said to be the identity relation. See here, it's going to be identity relation if and only if every element of set A is related to itself and only to itself. Okay, what does it mean? Let's say that I have here set A, okay, and here again set A. Now this type of relation, it is defined on set A. Okay, because why? Because every element must be related to itself, right? So it is defined on set A. So here you cannot do set A to set B. Why? Because we have to map, or we have to relate every element of this set, right, with itself, right? So here, if I have elements 1, 2, 3, then here I have to take 1, 2, 3. And it says that the relation from set A, this is the relation from set A to set A, or this is the relation on set A. So this is going to be identity relation if every element is related to itself. 1 is related with 1, 2 is related with 2, 3 is related with 3. Understand? So if R, it's a relation from A to A, right, on set A, then I can say here that R, it's going to contain the ordered pair AA for all A belongs to A. I hope you agree with it. So here, if I pair, so it's going to be 1, 1, 2, 2, and 3, 3. Right? Now, sorry, just keep dropping these markers. Okay, now what if they are related, the elements are related to itself, if every element is related to itself, and in addition to that, they are also related to some other element. Let's say that 1 is related to 1, 2 is related to 2, 3 is related to 3, but here 1 is related to 2, and 2 is also related with 3. Now, is it going to be the identity relation? No. That's what it says. If every element of set A is related to itself and only to itself, means that they, every element must be related to itself and only to itself. So if they are paired or related to some other element, okay, other than related with itself, then it's no longer going to, or it's no longer remain the the identity relation. So we cannot accept that. Okay, so here 1 should be related with only 1, 2 must be related with only 2, and 3 is related to only 3. Only then it's going to be the identity relation. I hope it is clear to you. Okay, now move to the next. So we'll do one more and then we are going to wind up this session. Okay. The next is our reflexive relation. Okay, number 5 is a reflexive relation. So number 5 is a reflexive relation. Okay, and what does it says? It says that relation is said to be reflexive if every element of set A is related to itself. Okay, now you will say that it is similar to identity relation, but it is not. We have to read it carefully and we have to understand what does it mean. Let's say that again. This type of relation, reflexive, it's going to be on the set A. Okay, so here let's say that I have set A, right, and here I have set A. Okay, so here I have elements 1, 2, 3. Here I have 1, 2, 3. Okay, and this relation R is on set A. Okay, so R is a relation defined on set A. Okay, so in reflexive relation, what happens is that the elements in set A, they are related to itself. Every element is related to itself. Plus, they can also be related to some other elements, means that 1 is related to 1, that's fine. 1 can also be in relation with 2. There is no problem with it. 2 can also be in relation with 3. There is no problem with it. Understand? Yes, the minimum condition for any relation to be reflexive is that every element must be related to itself, but these elements can be related to the other elements. There is no problem with it. Okay, so what I am trying to say here is that see here, from here I'm going to develop several relations. Let's say that R1, okay, uh, R1 is when only these elements are, when the elements here are just related with, every element is related with itself, which means that 1, 1, 2, 2, 2, 3, 3. Okay, is this reflexive? Yes, it is reflexive. That's what the definition says. Now let's say that R2 is the relation, and here I have 1, 1, 2, 2, 3, 3, right? As what this picture representation says. And in addition to this, I have here 1, 2, and here I have 2, 3. Then what about this? Yes, this relation is also the reflexive relation, because this is the minimum condition, it is there, and if it has some more additional ordered pairs that results from relating elements in this set with other elements in this set, then it is fine. Then can we allow it if 3 is also related with 1? Yes, of course, it is allowed here. So here it's going to be 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 3, 1. Okay, so I hope you understand the difference between identity and reflexive. Okay, it strictly says that every element must be related to itself and only to itself, but here it doesn't say only to itself. Okay, so it can accommodate other relations, okay, from the elements in this set to this set, okay, other than relation of every element with itself. Okay, so just keep this thing in your mind. Now from here we can say that all identity relation, now I can write it here, all identity relations are reflexive, but not all the reflexive relations are identity relation. Okay, so all identity relations, they are reflexive relations, but not all the reflexive relations are identity relations. Okay, now see here, so what's happening, if someone asks you that how many identity relations are possible from A to A, okay, so your answer must be one relation. Okay, so here I'm writing possible number of identity relations from A to A. Okay, so how many? Only one. Okay, so please keep this thing in your mind. Okay, so there is only one identity relation that is possible from set A to A. Okay, now we'll talk about how many equivalence relations are possible. Okay, to understand that, um, just I need your few minutes. Okay, okay. So how many reflexive relations are possible? Okay, now see here, let's say that, okay, uh, let's say that I have a set here. Okay, this A represents the set and its set of elements 1 2 3. Okay, or just keep it simple. Here A is the set. Okay, here A is the set where I have n numbers. Okay, n numbers, A2, A3, so on up to an. Okay, so A is the set of n numbers. Understand, A is the set of n numbers. So I can say that the number of elements in this set A, which is represented by NA, it's going to be n. Okay, so I hope you agree with me, right? Now, if I have to apply the reflexive relation on this set, then what it's going to be? Okay, so what's going to be the possible scenario? Let's see that. Okay, let's see that R is the reflexive relation that is defined from set A to set A. Okay, so if R is a relation defined from set A to set A, it means that this relation it's going to be subset of A Cartesian product A, right? Because that's what we say, that relation is the subset of the Cartesian product. Here we define this relation, reflexive relation, on set A. So this reflexive relation, it's going to be the Cartesian product, subset of Cartesian product A, right? A Cartesian product A. Okay, so if we do that, so now see here what's going to be A cross A. Okay, if we do that, then what we are going to get? So here we will get something like uh, A cross A. So we will get something like uh, A A1, right? A1, A2, A2, here A2, A3, right? Then we are going to get something like A1, A12, A1, A12, then A2, A22, right? Because we are just doing A cross A, so we have to make all the possible pairs of every element of this set with the same set, right? So it's going to be something like, or I can do one thing here. It will create some confusion here. Here, first of all, I can say that here it's going to be A1, A1, here A2, A2, so on up to AN, AN. Okay, why? Because here I have to figure out the reflexive relation here. That's why I have paired these type of elements first. Okay, and then also I'm going to have like A1, A2, right? Yes, A1, A2, then A1, A3, right? Then A2, A3, right? So on, something like A n minus 1 and 2A n, right? Okay, so I hope you agree with me. Is it visible? Yes, it is visible. Okay, so here I have n elements. Okay, and in if I have n elements in set A, then number of elements in A cross A, it's going to be n square. I hope you agree with me. Why? Because n of A Cartesian product A, it's going to be NA multiplied by NA. So which is going to be n square. Means that, what does it mean? It means that how many terms, sorry, how many elements are going to be in this A Cartesian product A, n square. Okay, now for this thing, okay, for this relation, okay, now see here, okay, here I have how many total terms? Total terms here, it's going to be the total terms here, sorry, the total elements here going to be n square. I hope you agree with me, right? And I want to develop a reflexive relation here, right? And I know it's going to be the subset of this set. So I know for this relation to be reflexive, I have to include all these ordered pairs, because that's what the definition says, that every element is related to itself, right? So means that these ones are important for me. Okay, only then this relation is going to be reflexive. Okay, so this is an okay, and how many elements are these? N elements. I hope you understand me, right? Now see here, this is the minimum condition, right? This is the minimum condition for this relation to be the reflexive, that it must contain all the elements that are related to itself, right? And how many elements are like that? N elements. Now see here, what about other elements? Now tell me, what is the possibility of this element A1, A2? It has two possibilities. Either it can come, or it will say that I'm not interested. Okay, if it comes, it's fine. If it doesn't come, it's fine too. Okay, so what does it mean? It means that it has two possibilities. What about this? It also has two possibilities. What about this? It also has two possibilities. What about this? It also has two possibilities. Either it can jump in, or will it will be happy here, right? It will say that, okay, I'm not getting in, better I stay outside, it's fine. Okay, so because n is here, so how many elements are going to be here that will decide that this thing is going to be reflexive? It's going to be n square. Now see here, total n square, right? N square elements. N came here. So how many are left here? So this is going to be your n square minus n, right? Because the total was n square. Okay, so it's going to be n square minus n. Now n square minus n elements have two possibilities. Either they can jump in and make it reflexive, or else they prefer to stay out of it. Okay, so if we use little bit of permutation combination here, then the total possibilities, it's going to be 2 raised to power n square minus n. Okay, for these elements to come in or stay out, in order to make this relation reflexive relation. Okay, so it means that the total, okay, total number of reflexive relations, total number of reflexive relation from set A, relations from from set A to relations on set A. On set A, it's going to be 2 raised to power n square minus 2. Okay, you can apply this formula here if this work out or not. Okay, now see here, uh, where is it? Okay, all right, so here we had this set, right? And here, how many elements do you have? Okay, so here my set was A, 1, 2, 3, right? So how many reflexive relations are possible here? It's going to be 2 raised to power n square minus n. What is n here? 3. So 2 raised to power 3 raised to exponent 2 minus 3. 2 raised to power 9 minus 3. 2 raised to power 6 means 64. Okay, yes, 64. 2 raised to power 8, yes, 64. 64 reflexive relations are possible for this set. I hope you understand it. Okay, so what does it mean? It means that you can create 64 reflexive relations from A to A or on set A. Okay, so total number of reflexive relations, it's going to be 2 n square minus n, where n denote the number of elements in the set. Let's say that the given set is let's say that the given set is A, and it has 2 elements, 1, 2. Okay, so how many reflexive relations are possible? 2 raised to power 4 minus 2, and which is 2 raised to power 2, which is 4. Right? And what could that be? Can you tell me what could that be for? So see here, it's going to be 1, 1, 2, 2, right? 1, 2, 1, 2, 1, 1, 2, 2, 1, 2, 2, 1, right? 1, 2, and here 2, 1. So 1, 2, 3, 4. So see here 4. So means that this is valid. Okay, so always remember how many identity relations are possible on set A, only 1, and how many reflexive relations are possible on set A, 2 raised to power n square minus 2. Just n is the number of elements in the set, just put the value and you will get it. Okay, so here I have shown you it has just 2 elements, so you can even see with the visual representation. Okay, where I have mapped, and in the end I got 4 ordered pairs. Okay, so that's how you have to do it. I hope you understand it. We are left with few more relations which we are going to discuss in the next session. That's all for today. Thank you very much. Have a great time. Bye bye.